These are the laws that we kind of briefly mentioned when we talked about the understanding of the universe. So now we're going to talk about them in more detail so we know exactly what those are. First of all, let's talk about what a scientific law is. It is a description of a naturally reoccurring event. It's almost always described in mathematical terms. It does not describe how or why it works. So it describes like a theory on gravity would the law of gravity would describe it in mathematical terms. It doesn't describe why gravity works. That is completely would be the theory. So that's the difference between the theories and the laws. Isaac Newton's law of universal gravitation. Every object in the universe attracts every other object. Part A, the more mass an object has, the greater its gravity. And part B, the closer two objects are together, the greater the force of gravity is between them. And here it is in the actual math form. So the force of one equals the force of two, and G is a gravitational constant, which you can look up. And then you have mass one times the mass of two divided by the distance between them. Does this remind you of something we just finished? We just finished the what? The Orbits VLab. We should have seen this in actual simulation, obviously, because in the real world, we can't adjust the size of the sun or the size of the planet, right? But that's the bonus part of being a virtual lab. We had the option of changing things around and actually seeing that. Newton's first law of motion: an object in motion will stay in motion unless acted upon by an outside force. So the desk that you sit in doesn't move by itself, right? Unless someone kicks it, bumps into it. That's just, well, that'd be the second part actually. An object at rest stays at rest unless acted upon by an outside force. Now you may think, but wait a second. When someone bumps my desk, it doesn't stay in motion forever, right? That's because there are the outside forces. There's gravity for one. There's friction for another, the friction of the desk on the floor, and of course, the main force, gravity. So we saw that when we watched the MythBusters, right? When they took it to into the vacuum, we saw the flag, for example. It moved a lot more inside the vacuum because the friction was a lot less. Now, on the other hand, it did slow down because it was being acted upon by gravity. So again, as long as there's outside forces, you're going to see the motion slow down or eventually stop because of the outside forces. So thinking about this, the protostar, when it starts, it's rotating and it doesn't get to start that rotation until energy is put into it, right? And then as that energy is started and it's rotating, how does that relate to our planets and why they're still rotating today? It's directly related to that first law. The planets in motion stay in motion because there's no friction in space, and the gravity keeps them rotating around the sun. So that's directly related to that first law. Kepler's first law has to do with proving that the planets are orbiting in the ellipse with the sun as one of the focus. So even though it looks like the Earth is going around the sun in a perfect circle, it's not quite perfect. It is a slightly squished circle. In other words, it is an ellipse. Kepler's second law: the planets move faster when they are closer to the sun and slower when they are further away. So there's times of the year when we are closer to the sun and we do move a little bit faster, and that's called the perihelion. And then when we're further away, it's called the apohelion. We saw this when we changed the distance of the Earth to the sun. It was much more apparent when we were closer to the sun, but it does still happen. Kepler's third law allows us to calculate the planet's distance from the sun even as long as we know the planet's orbital period. So if we can watch how long it takes for any planet to go all the way around a star, so it can be our star or it can be the exoplanets going around their star, we can calculate how far that planet is away from their star. And let me move myself. And so we can see that it is a lies straight along a line, and we can do this for any star. Like I said, any star, it does not have to be our star. And that's how we can calculate, like if you see information about exoplanets, we are doing this by watching how long it takes for that planet to go all the way around its star, and then we just figure out this. And there's other ways to calculate, like if it takes a really long time for it to go around its star, we can do calculations that let us figure out faster than 100 years. Okay, we're already on Einstein's theory of relativity. We're almost done. Like we said the other day, is classically expressed as E equals mc squared, where E is energy, m is mass, and c is the constant of light. Again, something that we can easily look up, and that's the speed of light squared. And this is a big deal because it helps us understand how energy from the Big Bang became mass as it slowed down, and therefore giving us the whole idea that the Big Bang can actually be the cause of the universe, as it may be. Hubble's law. So, not only did Hubble discover that there were other galaxies in the universe, but he discovered that they were moving further away from each other, that most galaxies are moving further away from each other. So, the further the galaxies are away, the faster they're moving away from us. And so, again, he's got this as a mathematical equation where v is velocity, how fast you're going, right? Right, miles per hour is a velocity. But in this case, we have Hubble's constant times the distance that particular galaxy is away from us. And I'm not going to make you memorize any of these or do math in any sense, but I just want you to understand that these are equations in a mathematical sense, and that this is how the astrophysicists work with these numbers and such. And that is all I have for today, and I will talk to you soon.